And so it says if you have our function f of x equals a times b to the x, if a is greater than 1, sorry, if a is greater than 0 and b is greater than 1, then we can say that that will be an exponential growth function, right? Just like we drew out yesterday, it will look something like that. And we can say that base is the growth factor. If you change it around and you make a is still greater than 0, but b is less than 1, then you're going to get an exponential decay function that looks like this. If you ever get confused whether you're dealing with growth or decay, I think the easiest thing to do is pick a couple points and see what's happening. As x is getting bigger, is y getting bigger? That's exponential growth. Or as x is getting bigger, is y getting smaller? That's decay. They try to trick you a little bit with some extra negatives or writing with exponents a different way, but this is the basic rules there for growth and decay. When they give you a story problem, I think it's much easier because they talk about population growing or population declining, or they talk about whatever the half-life stuff, and they tell you it kind of in the problem that you know what's happening. The harder ones are the ones that aren't story problems, like the examples here in the first couple problems on your homework that say state whether the function is exponential growth or exponential decay. We'll talk about maybe ways that you could do this, or ways if you get stuck that you could do this. So 3 to the negative 2x. We take our rule over here. Oh, I don't want this here. It talks about b being greater than 1 and b being less than 1 to the x power, right? A times b to the x power. So I wanted to show you that the book gives you that rule, and then sometimes you get a little, you get tricked on this, because this is b. Do you agree with me? B is greater than 1 there. Look at our exponent. Our exponent's a negative. We talk about that in the little rules there. So I just wanted to caution you on going straight off those rules over there on how you would do this. If I keep plugging in bigger numbers for x on that, what's going to happen to my y value? It's going to get smaller because of this negative right here. So if you see a negative exponent, it doesn't always mean decay, because it could be a trick also, because then what if this was negative? Oh man, it gets a little crazy. But you want to think about what's happening. So I'm going to say as x gets bigger, f of x is decreasing, or f of x is getting smaller. So that means that number 1 is exponential decay. And I always say, if you're not sure, just pick a couple points and see what happens. Or plug 10 in there, and if it's growth, you should get a pretty big number. If it's decay, you should get a really small number. So think about number 2 for a minute, and think about whether you want to say number 2 is growth or decay. The book talks about limits with this stuff again, which limits are just saying like what's happening as x is getting really big, is y getting really big, or is y getting really small. So you don't really have to talk about the words limits when you say that. You can kind of just talk about this. So does anybody have a thought on this, growth or decay, and the reason why? You can whip the calculators out. That's a good idea. If you're not sure, take some numbers. Could I rewrite 1 over e as an exponent instead of as a fraction? What would that be if I wrote this as e to the negative 1? So that would be the same as e to the negative x. If you write it like that, does that help any? Does that make you think growth or decay? That still doesn't help. Pick some numbers. Pick 10 for x and see what you get for y. If that's a growth factor or a growth function, then you should get a really big number for y. Or if you do e to the negative 10, is that going to be a really big number or a really small number? the 10th? So this is going to be really small. Probably gives it to you in scientific notation, I would say. Really small. Close to 0. So if this is really small, what does this mean? It's exponentially negative. Okay, so you have a couple problems on your homework. Definitely check the auto look at the back as you're going through it and see if you're making sense of it as we go through there. Okay? The only other example that I have today for you is for a little philosophy application. We're just doing one. It says the population in Ohio can be modeled by this lovely function. This is a logistic function. We talked about those in our 10 graphs that we did. Eventually, later in the chapter, we're going to solve this, like solve it for t, and do all the math to get there, but today we're not going to do that. It says P is the population in millions, and T is the number of years since 1900. How many people were there in 1950? What would you do to this equation if you wanted to find how many people were there in 1950? Yeah, it says T is the number of years since 1900. So 1950 is telling us that T equals 50, which means this is kind of a big calculator problem where you can do this all in one step if you do it correctly typing it in, or you can do it in a couple steps to get your answer here. So if you don't have a calculator, just like yesterday, I'm going to give you one because part of this chapter is being able to use a calculator correctly. So who needs a calculator? Matt, do you want to use my calculator? You're like, hey Joe, you need to have backwards calculator, don't you? We have to do everything the opposite way. That's what calculator I had in school, and it was awesome. But now that there's these calculators, I feel like it's harder to get. Like it's harder to type it all at once. Do you agree with that? You just have to write things down. Oh, okay. Let's see. So if I do this, it's nice I put parentheses down here already for you. If you're typing something in with addition and subtraction in a fraction all at once, you must use parentheses. If you're worried about that, you can do the bottom first, write your answer down, and then take 12.79 divided by that answer, or go back and find that answer. I do want to talk about, like, if you're going to do it step by step, there's something called round off error, which means don't round until the end. Like, write all those decimals down as you go. But I think we can just type this in. I want to type mine in all at once. See if I get the same answer. 1 plus 402 times 50. And if you don't close your parenthesis at the end of this, it's okay because you're at the end of it. If you're writing something after it, it would be really important that you close the parenthesis. But I got 8.4568966. 230. And so Maddie said that doesn't seem like enough people, but what did you notice, Maddie? It says in millions, so we really could say, that's why I wrote all these numbers down. We could really say 8,456,000 people, 897 if I rounded, right? Or you could say like 8.5 million, right, if you want to round to that. But it is kind of important that you notice that it was in millions, that you don't say 8 people. You could say about 8.5 million people. Did anyone not get that and want me to help them with their calculator? Okay, then look at part B. It says, when was the population 10 million? There's math that we can do that we're going to do later in this chapter that we could actually solve this equation, but we're not there yet in this chapter. But when the population was 10 million, that's like setting this equal to 10, right? We want to know when we would set that equal to 10. We could graph it and do that. We're going to do that next week, maybe later this week. But today, I think today we could just do some guess and check of if I fixed t values and looked at the population, should I pick higher than 1950 or lower than 1950? Higher, because I already know in 1950 there were like 8.5 million. So let's pick another number and plug it in and see if we can get 10 million. So what do you think? Go 1960. Anybody got a guess? 1960. And you just, the nice thing on my calculators too, I don't know if yours do this or not, but you can go back up to that whole equation that you just typed in, and you can just change 50 to 60, and then you don't have to retype it in. If you don't know how to do that, let me know and I can show you, so it saves you a lot of time. So if I do 1960, I got 9.29 million. I'm going to do 1970. I got 10.02. Should we check 1969? We think that didn't happen in 1969. 9.95. Now you see how we just kind of honed in on the right answer there? When was the population 10 million? Did we say 1970? Did we say 1969? 1970. I'm going to say 1970. You could argue like is it at the beginning of 1970? Because really if it was 10.02 on January 1st, but it really was 10 before that, right? You could argue the logistics of it all. But I think you could say in about 1970. And again, like I said, eventually we're going to be able to solve these where we do all the math to undo that, and it's so exciting to do that. And even later in this week, or beginning of next week, we'll graph these and talk about if you graphed 10 million and you graph this equation, you can see where they cross, and you don't have to just guess and check to do that as well. All right? So, 3-1 day 2, we will go over this on Thursday, because tomorrow, even though seniors will be here, juniors won't. But this is your assignment. There's some story problems. There's some problems at the beginning about growth and decay. The story problems are very similar to the ones that we did, and then there's a couple multiple choice about exponential functions. So really not that much work, especially compared to day 1 that we did. The other thing is I'm going to pass your test back. So let me do that, and then we'll talk about them for a minute. And then you have some time to work. So you can either choose to work on test corrections or to work on your homework. Oh, I'm sorry. So remember that test corrections are for grade. I think it's important that you fix what you missed, even if you didn't miss very much. I think it's important to learn from what you mistakes you made. If you don't know what mistakes you made, you're welcome to talk to other people. You're welcome to talk to me. You're welcome to come in before school, after school, 7th period. Let me know what time that works for you, and I can help you. I can even let you during a study hall if you want to borrow my answer key to look at it to see what you did wrong. To do that. I will give you the answers. I just want to know that you understand what you missed, right? That's the number one thing I look at when I do test corrections is the middle part. What did you do wrong? Because you want to make sure you know that. The retest, very similar to this, which means if you understand what you did wrong, then you can retake that anytime between now and next week. I can even go to next Wednesday as opposed to next Tuesday since juniors are kind of losing a day with this. Little things that people missed. Linear factorization, right? It gave me the zeros instead of the linear factors on number 2. Number 3 and number 4, a lot of people missed points on that for either forgetting your y, forgetting to multiply it out, forgetting the other conjugate. If you need help on those, just ask me. and I will help you as we do those. Middle ones, 8 and 9. If you didn't check your answers, you missed a point there. A lot of people on 9 like didn't distribute that negative sign. I'll tell you that. Like, see where it says minus 4 over x minus 1? I tried to circle if you put, like, I think if you got minus 20 up there in that problem, you just subtracted, like, it should have been minus 12, not plus 12, or the other way around. It should have been plus 12 and not minus 12. You just didn't distribute your negative sign, which isn't a huge deal, which is why you didn't miss a ton of points. But you got to watch those negative signs as we go there. If you missed 5, 6, and 7 about asymptotes, see me. I can help you talk about those rules. But a lot of people still miss the slant asymptotes. A lot of people on number 7 like didn't factor the denominator. Just take out of 2x. 7 equals 0. I'm not going to work all these out here, but I will tell you number 14. You can't have a domain with imaginary numbers, and it really threw a lot of people. We did a couple like that when we talked about domain at the beginning of this chapter. If the domains, you get an imaginary number on your domain, it just means the domain's all real numbers, right? If you get imaginary, it means, oh, x can be any number. So number 14, the answer should have been all real numbers. The extra credit, if you got the first extra credit, all worked out with all 4 zeros. You got 5 extra credit points, which was kind of cool. And then the second one, you had to do some long division with and get fractions, and that was a really tough question. If you're interested in knowing how to do it, I'd be happy to show you. We have, what time do we have here today? 55. So it's 15 minutes. So if you have test questions and you want to ask me often, I'll be happy to do that. If you just want to start on this homework, or you want to start on your test corrections, I would be happy to do that. Does anybody need the format for test corrections again? The number you missed, why you missed it, and rework it, right? That's pretty much the format. I haven't put these in the grade book, so if people don't need me, then I'm going to work on getting grades updated. Okay? Okay. Let me stop recording this.